Good morning and welcome back into our new and maybe improved reality for at least this part of the year. Um, we will be continuing to do the next few chapters, but before we get there, because they're all about inference and confidence intervals, I wanted to go back and review Chapter 10, which seems like it was so long ago, because Chapter 10 really set up the basis for the tests of significance and confidence intervals. And all that stuff's going to continue. We're just going to learn a couple more types of tests and intervals for, say, when we have two sets of data, like when we did the paper airplanes. Or if we don't know the population standard deviation, what do we do? But it all comes back to basically the same stuff with very, very small changes. So what we know so far about inference. Confidence intervals. That's kind of where we started. What are they? Confidence intervals estimate the population based on the sample. Right? We have a sample, we get that, oh, the mean is 12. Well, the mean's 12 plus or minus that little bit. Like the mean of the population isn't 12. That's a good estimate, but we need to include that margin of error. It's not a probability. The mean or proportion or whatever the parameter is either in the interval or it's not. We might be 95% confident that it's in the interval, but it is not in the interval 95% of the time. That would be an incorrect statement. 95% of the intervals we could have gotten would include the parameter. There are two parts of the confidence interval. We have the confidence level, 95% certain. 95, remember, is kind of the standard confidence interval. It's nothing super special, but it's just kind of the go-to. And then the interval. And the interval consists of an estimate plus or minus that margin of error. So the ones that we know so far are the z-intervals for sample means. We can do proportions as well, and I think we kind of touched on that a little bit, but that'll come up a little bit later. But the z-intervals, that's what we've found with the z-score and stuff like that. And I mentioned z-intervals because in the next couple chapters we're going to get t-intervals and chi-squared intervals and things like that. So it's just a different type. The z is specifically when we know the population standard deviation. That's what differentiates it from, say, the t-interval. So we have conditions. The data is from an SRS. That will be a condition for all of these. Also, the sampling distribution of X bar is approximately normal. We'll see how to check that or verify that in a minute. And then specifically for Z, we know the population standard deviation. The other two are going to be a consistent thing for pretty much all of these. The population standard deviation says we're using Z instead of some other test that we don't know yet. The formula, we get X bar plus or minus a Z star times sigma over root n. That would be our estimate is the X bar, and then the plus or minus part is the margin of error. That's how far are we going. The Z star, remember, is talking about how many standard deviations it is away from the mean. We get that based on the confidence level. We're going to see a couple more Z's. The Z star we pick, again, because we pick the confidence level. As opposed to the Z score that we'll get for the test, which we find based on our data. To check for normality, there's a couple different ways of doing this. The first way, you can check the data with a stem plot or a histogram. They're basically the same thing, and a normal probability plot. With the stem plot or histogram, we're looking to see that it's basically symmetric and normal shaped. And then a normal probability plot, we're looking for it to be roughly linear with most of the points kind of clustered around that center. The magic phrase when you're checking normality is we're not looking to test to see if it's normal or not, because we can't test that with only that small amount of data. But we're looking for not clearly non-normal, which is just such a fun phrase. I love that one. And so it's like, hey, it doesn't look like it's not normal, so it's not clearly non-normal, so we can go ahead and use the test. If the sample size is big enough, you could also use the central limit theorem, which says that if the sample size is big enough, then the sample distribution will be approximately normal. Again, that was from the last chapter, and how big is big enough? Well, it depends on what the population looked like, but if you have a sample of like 50 or so, it should be big enough for pretty much any population distribution. Well, that was awkward. So choosing your sample size. We want to choose a sample size sometimes. Sometimes we're not given the option, but we can choose a sample size to make that margin of error what we want it to be, because the z-star is going to be fixed based on our confidence level. The population standard deviation is going to be basically fixed, so that root n, we can adjust it so that we can have a margin of error that's small enough to make what we're doing worthwhile. Again, if you get the height of an average high school student is 5'10" plus or minus 1.5 feet, that's really not going to do you any good. You want to get that margin of error down so that you have a decent estimate of the population. So to do that, you just pick what you want your margin of error to be. Hey, we want to be within 2 inches. So we have 2 inches equals the z-star times sigma over root n, then you just solve for n. Significance tests, as opposed to confidence intervals, which estimate the mean. The significance test tests a claim against a population. Now that could be a bunch of different ways. We could know that the average high school student's height in the US is 5'10", and we think that Stanwood is shorter than that, or taller than that, or just not 5'10". So that would be the claim against our population. We're thinking that maybe we're not the same as the rest of the United States. A significance test returns a p-value. The p-value is the probability of getting the data that we got if the null hypothesis is true. And so the smaller the p-value, the more evidence there will be against that null hypothesis, because if we get a p-value of 0.7, well, hey, that's 70% of the time, if the null hypothesis is true, we'll get the data we got. But when it gets small, usually our cutoff there is going to be about 0.05. That means only 5% of the time, if the null hypothesis is true, we would get the data that we got purely by chance. The goal of a significance test is generally to reject the null hypothesis. Now, that doesn't mean that you are really trying to, but that's kind of the goal. Just like the goal of the prosecutor in the court is to prove the person is guilty. And then our two options are there is enough evidence to reject H0, or there's not enough evidence to reject H0. We never accept the null hypothesis, generally speaking. We either reject or we do not reject. Just like, again, in court, the person's either found guilty or not guilty. You never are found innocent. That's not one of the options. Now, you can take this to multiple levels. Instead of this, there is enough evidence to reject H0, there could be strong evidence to reject the null hypothesis, but those are still the two options. So now to the ones that we've done z-tests for population means, just like we did the z confidence intervals. That's what chapter 10 was about. So our conditions, we have a sample is an SRS from the population again. The sample distribution is approximately normal, and we know sigma, the population standard deviation. Again, that determines that we're using a z-test instead of some other type of test. The equation for this, our z, and this would be the z-score as opposed to Z star, which we chose based on confidence level for our confidence intervals. This Z score we get from the data, and we get it by X bar, that's the mean from our data, minus mu naught, that would be from our null hypothesis, we'll see that in a minute, divided by sigma over root n. The Z value you can actually use kind of like a p-value. They're basically the same. The Z is the number of standard deviations away from the mean it is. It correlates directly with a p-value. The higher the Z, the more unlikely it will be. So the higher the Z, the lower the p. But we take that Z value and we take it to table A to find the p-value. Now remember, depending on which way you go, you may have to do 1 minus in order to get there. Chances are your p-value will be less than half. So if you get a p-value and it's like, oh, it's 0.87, you probably need to go 1 minus that, is a rule of thumb. Otherwise, your data and your null hypothesis is going to be super close together, and you'd feel silly doing any of this stuff in the first place. Our inference toolbox, remember, anytime we're doing inference, we want to follow these same basic 4 steps. The first one, identify the population of interest and state your hypotheses. Now, if you're doing a confidence interval, you don't have hypotheses, but you still want to identify the population of interest. Step 2, choose the appropriate test or interval. If you're doing confidence interval, right now we have Z tests and Z intervals, but we will be getting more here very shortly. And then check the conditions. Checking the conditions is very important. And when you choose the appropriate test, you can name it by name or by equation. So for this one, we could go, hey, it's a Z test for population means. Or you could write down Z equals X bar minus mu over sigma over root n. In this case, it doesn't make that much of a difference. Some of the later tests that we'll find, or that we'll learn, have crazy equations that you don't want to write out. Then step 3, carry out the inference. This could be done using your calculator, could be done on paper. That's up to you depending on what you have, but you want to make sure that you remember how to do it using your calculator. The only things that actually need to get written down in step 3 are your test statistic, which would, in this case, be your Z value. So we'd have Z equals 2.7, P equals 0.048. I don't know if those two go together, but that's what you'd have, your test statistic and your p-value. And then finally, interpret your results in context. You should be able to read this last part and know exactly what your problem was talking about. More on some significance tests are hypotheses. We have 2 of them. The first one's a null hypothesis, which is written as H naught equals, or H naught then a colon, mu equals, this is always done in terms of the population parameters, not part of the statistic. It's not X bar equals, we know what X bar equals, we don't need to hypothesize about that. And then the alternative hypothesis will be the same, except we won't use equals. We'll use greater than, or less than, or not equal to. So on these, our hypotheses, we could have H naught mu equals 7. And then HA, mu is greater than 7. If 7 was our thing. These 2 pieces are always the same. It's only the sign that is different. Significance. That is it different enough? We have significance levels. And that, again, is that threshold. Like, what is unlikely enough for it to count? The variable we use for that is alpha. And the standard significance level is alpha equals 0.05. Now, that's not a hard and fast thing. You can have smaller ones or bigger ones. I've seen 0.01. I've seen 0.1. It all depends on how unlikely it is or improbable it is. How much evidence do you need against that null hypothesis to prove your point? 5%, 0.05 is just kind of the standard. It's 1/20th. So 1 out of every 20 times we could get those results. So that's just kind of what's used. But remember that the difference between 0.049 and 0.051 is nothing. Like there's no real difference there. So just because it's 0.051 doesn't mean that it's not unlikely, but if you have to have that cutoff, you do have to have that cutoff. Statistical significance, if the p-value is less than that, it's called statistically significant, which means that it has, like our test returned results where we can reject the null hypothesis. Remember that statistical significance is not necessarily the same thing as practical significance, because we could have a sample size so big that that difference is basically nothing, and yet it'll still return those results. So you always want to be paying attention to your data. Don't just blindly do tests. Errors. We have a couple different types of errors. Type 1 error is rejecting the null hypothesis when it is in fact true. The probability of that is just the alpha level, because that's the likelihood of getting those results if it's true. And so if we get that, the type 1 error is just the alpha level. The type 2 error is not rejecting the null hypothesis when it is false. And the probability for this is a little bit more complicated. We'll talk about that on the next slide just a little bit. But remember, we also have this in your notes, so you can always go back to your notes and see this. And then the power of a test is the probability that the null hypothesis will be rejected when it is supposed to be rejected. And we can find that power by just doing 1 minus the probability of the type 2 error. A nice little graphic here. This shows you where those errors happen based on our decision and the actual truth about the population, which we don't know. So you get your type 1, type 2 errors. So that type 2 error, we have our basic, or our population curve, or what we think it is, and then we have an alternative one over here. And so we want to know the probability of not rejecting the null hypothesis when we should. And so to find this, we have to find the values that would cause us to reject the null hypothesis in our original curve. There's one on the top, one on the bottom because of the symmetry, but really only one of these is going to be used because this area for the second curve down here is 0 for all intents and purposes. So we don't even need to worry about that one. But we find this value, and then from there we have to use the second curve and figure out what's the probability that it's going to be in this area over here. So to do that, we can set it up. The very first one, our null hypothesis is 2. So we can get our z value is going to be x bar minus 2 over the standard deviation for this problem happens to be 0.1. And then root 50. The z, in order to reject it at a 90 or a 5% level, remember that 1.96, that's that z. And so we have to do it for both sides because we have this one would be negative 1.96. We're not really going to go down there. We'll just do it for the positive one. 1.96 equals x bar minus 2 over 0.1 over 50. We can solve here for x bar. So you do a couple little mathing deals, and we get that x bar here is going to equal 2.0277. So that is going to be this value here, this critical value of x bar that's talking about. Because anything above that, we would reject the null hypothesis. Anything below that, we would accept the null hypothesis. So now we want to know what's the probability of accepting this if this other null hypothesis, this 2.05, is true. So we're going to now do the same basic calculations, but we're going to find the probability. So now we're going to find z equals, we have our 2.0277 minus this new hypothesis, 2.05, over, then we have the same 0.1, not 0.01, 0.1 over root 50. We can do the subtraction, division. We get z equals negative 1.58. We can take that to table A to get the probability. That p-value equals 0.0571. And that was a, we probably would have had, no, that would have come out exactly like that because it was on the bottom side. So we get the probability as 0.0571. So that is the probability of a type 2 error. The power, which is usually what you're asked to find, is going to be 1 minus is 0.0571, which would be what, 0.9429. Or so. So that's the process of a type 2 error. I would definitely practice it a few times. It doesn't come up a lot in the next couple chapters, but there's almost always at least one problem on the AP test that involves something like this. So it's definitely something you want to look at. But this was a review of all of chapter 10, what we know about inference so far. We will be starting with chapter 11 next, and going a little bit, hopefully not quite so much in each of the videos. So until next time, keep working problems, keep asking questions, and as always, happy mathing.